Welcome back to our AP Chemistry Chapter 14 notes over kinetics. We're going to, in this section, look at a lot of things about the nature of the reactants and how the reactants are of importance when we discuss rates. This is not something that is directly tested on the test often, but it is very important for your overall understanding of some of the main key basic ideas of what really needs to occur for a reaction to occur when these collisions are made. And I want to start off with an example of what it would take on the atomic level for reactants to react. And so we're going to turn to our good old friends, the Mythbusters.
Everything goes right, and that stuff goes up in the air, and it actually ignites, we could set this whole hillside on fire.
I'm either expecting to see a much bigger mushroom cloud of fire, or because it's heavier, we're going to see bloop, and it's going to catch on fire, and then we're going to stand there and watch it burn out. Hopefully, choice A.
Grant slowly builds the air pressure to 120.
Good to go.
Then Tori sets the spark. The mass of the creamer in relation to the volume of air is crucial. This could either be a blast or a burn.
All right, fire this puppy up. All right, here we go. Non-dairy creamer cannon in 3, 2, 1. That was frightening.
Terrifying!
Did you get that on high speed?
Yeah, we did remember to push the on button on the off chance that this might be one of the biggest fireballs ever.
This was frightening. I mean, seriously, there was a moment where I'm like, oh, crap, this was a bad idea.
All I heard in my head was run. And I started up the hill as fast as I could go. And I'm still on a little bit of adrenaline buzz right now.
Dude, you gotta feel this. It's like the top of a creme brulee.
Oh my God.
I think you need a new camera.
Should we take that off? It's still rolling? Oh, look at that.
Whoa!
Oh, it saved it!
Hey! You don't need a new limb.
This viral video is twice confirmed. The flame the governor must have seen from Sacramento. But it's not a recommended science project.
We should destroy this because it's too dangerous to have in our shop. This technology should not be shared with anyone.
And just in case you missed the message,
I hope I don't need to tell you this, but don't try this at home. We still have like 500 pounds of this stuff. Should we try it again?
Maybe after I get some new underwear.
So one of the things I love best about this clip is their reaction. Because I'd be like, yeah, expected it to do that. But they, of course, were taken by surprise. But what I want you to consider is what it would take on the atomic level for the reactants to react. What did it take for that reaction to actually occur? Okay, so I'm going to try to, we're going to watch it again for just a moment. And I want to point some things out. Maybe.
Everything goes
Here we go.
right, and that stuff goes up in the air, and it actually ignites, we could set this whole hillside on fire.
I'm either expecting to see a much bigger mushroom cloud of fire, or because it's heavier, we're going to see bloop, and it's going to catch on fire, and then we're going to stand there and watch it burn out. Hopefully, choice A.
Grant slowly builds the air pressure to 120.
Good to go.
Then Tori sets the spark.
Okay, so notice that. He lights a flare that's going to burn for quite some time, and he just shoves it right into the non-dairy creamer. And we just saw the non-dairy creamer become a massively huge fireball. And you're wondering, well, why is he putting it in there? Well, that's exactly the question I have for you. Why is it not already setting on fire? Now, what is key is understanding the phase of matter of the non-dairy creamer. It is a solid at this point in time, and it is well packed inside this large drum container. So not only is it unlikely that that light is going to touch at the moment in the non-dairy creamer, even if it were to touch that, we need oxygen for the flame to happen. For a fire, we need oxygen. We have our fuel source, the non-dairy creamer. We have our ignition source or heat source. We have the flare, but we don't have the oxygen in there yet. So what's it take to get the oxygen in there?
Mass of the creamer in relation to the volume of air is crucial. This could either be a blast or a burn.
So notice, still no oxygen.
Fire this puppy up. All right, here we go. Non-dairy creamer cannon. In 3, 2, 1.
Okay, notice it's going into the air. So you're like, oh, now we're getting some oxygen. Well, it's not on fire yet, so apparently we don't have enough oxygen yet. Okay, now you start to see the very tip of what's starting to happen there. Okay, there's another view of it. So still lots of just dairy creamer, solid dairy creamer going up in the air and about to fall back down. Why is it not lighting on fire when we know it's going to light on fire very well? It deals with the fact that right now the non-dairy creamer is so dense with itself that there's still not enough room for the oxygen going on. So the nature of the reactants is very important. And then there we get the fireball. Once we get the right ratio going on and it's aerated enough to allow the oxygen in so the fire can burn. Okay, we're done with that. We're moving on because we've seen it like 1.5 times now. So what's it take to facilitate a reaction, to make it go better? Well, the atoms need to be mobile, and they need to have high surface area. And so what situations have the conditions where they're mobile and where the atoms can touch each other and have high surface area? Well, the best of all situations, I hope you're thinking in your head, is gases. Gases are very mobile and have high amounts of surface area. They're able to be like not blocked by anything else around it because those atoms are very far apart. Okay. Now, of course, if gas phase is not possible, liquid phase is not bad, but now we're going to not have like that all surfaces. If there's some more molecules packed in around here for the liquid, even though they're able to be mobile, okay, this side is open, this side of that particular molecule not so open anymore. Okay, so it's going to react slower, and then of course a solid, being compact, would react the slowest of all. So most chemical reactions are also redox reactions. So if we had low ionization energies, that would help. Now why? What is an ionization energy? Remember, that's the energy to remove electrons. So if we have energies low enough to remove electrons, we are more likely to get a successful reaction when they react. That is very similar in this case, the ionization energy could be equated to the activation energy. If that's the only thing that occurs in the reaction is a losing of electrons, then the ionization energy is the activation energy. So what is the nature part of the nature of the reactants? When we say the nature of reactants is important, we're talking phase. Phase is very, very, very important. The other thing we could be talking is what activation energy is needed for that particular reaction. Is it we need some ionization energy? Is it dealing with electron affinities? Is there even more of that to it? And we certainly would be talking things like, are the molecules able to be collided on all sides? Are they blocked by some sides? So all those things play into the nature of the reactants. Okay, so now that we've talked about the nature of the reactants, I want to talk about the concentration of the reactants. So we're going to watch this video of burning steel wool, which, by the way, is mostly iron. It really isn't a whole lot of steel. So this is a flask of pure oxygen. Alright, so they lit it on fire, the steel wool, and it burned pretty well. But then the moment they stuck it into the flask, it burned very well. Why is it that it burned very well the moment they stuck it into the flask? Okay, well again, we're going to be looking at the concentration. The flask was concentrated oxygen, as opposed to air, which is about maybe 16 or so percent oxygen. So with a lot more oxygen around, a lot more likely that the collisions will be successful, because in order to react in this manner, the iron molecules had to collide with oxygen molecules, and then it forms iron 3 oxide or iron 2 oxide, depending on what the exact combination is. So the concentration of reactants has a huge effect on the rate of the reaction. We just saw that. We witnessed that in that flask. So it is very common for us to show this by showing what we call a rate equation or a rate law equation or something like that, where we relate the rate, the speed of the reaction. This is just a general term here. The rate of the reaction is equal to some rate constant, and we'll come back to this guy in a little bit, times all of the reactants. Okay, and this is square brackets, so that's going to be concentration. What's concentration measured in? Okay, seriously, what is concentration measured in? Please tell me molarity, which is capital M, which stands for moles per liter. Okay, so all of these are the concentrations. And then these X, Y, and Z are going to be these things that we will be working with called orders. They're not exactly exponents, but they do work in a very similar manner. But we refer to them order in a rate law. And so we would talk about A is to the order of X, B is to the order of Y, and C is to the order of Z. And then all together, we could add that all up together, have X, Y, Z, and then that would be the order of the overall reaction. Now, before we continue and show you how to find those orders, that's eventually what we're going to work on, I want to make it very clear from the beginning. These little superscripts, the orders, do not come from the coefficients in the balanced chemical equation. You cannot take an overall balanced chemical equation and assume these numbers from any part of that. If they happen to match, it is pure coincidence. We would need more information than just the overall balanced equation to figure out those orders. And of course it doesn't. There we go. So let's look at an example. So in this example, I have one single reactant forming two products. And the rate was determined by experiment to be equal to K, some rate constant, lowercase k, times the concentration of nitrogen monoxide, okay, so that reactant is there, to the second order. So our vocabulary is the reaction is second order overall, or second order with respect to nitrogen monoxide. And because there's nothing else in the equation, it's also second order overall. Now this does work as an exponent. So if we doubled the NO, if I put a 2 in there, it'd be 2 squared. That means we would increase the rate by 4. So doubling that would make the reaction go 4 times faster. Now you see the usefulness of knowing the order. It would tell us how to make it go faster. Okay, but I want to point out, to know those numbers, you have to do it experimentally. Now before I move on, I do want to ask, why don't the products appear in the rate law? Well, it does simplify to not have the products involved in the rate law. But again, what is dependent on the rate of the reaction? The reactants reacting. Okay. If we were putting in products, we could figure that out. We've done that before, like way back at the beginning. We could say if this is disappearing, this is appearing. So it really would also then be redundant. So we really should not be seeing the products involved. We should be seeing the reactants only involved, because those are the ones that are reacting. Okay, so let's look at another example. So here I have nitrogen dioxide and fluorine forming whatever that is. And we see that the rate was determined, so someone else did the experiment and found this. What is this saying? This is saying it's first order to nitrogen dioxide. And if you want to put a 1 there to not forget there's a 1 there, that is great. They will have no problem with that on the test, as far as I know. You can put a 1 there. And then it also seems to be first order with respect to fluorine. What is it overall? Well, it's 1 plus 1, so that means it's second order overall. So overall, well, let's get to that later. What would happen to the rate if NO2 was doubled? Well, if this is 2 doubled, but this stays the same, 1, then it's going to, overall, it's going to double, okay? What if we double both? Well, now, if that's 2 and this is 2, 2 times 2 is 4. Now, why am I not going to any exponent? Because the exponent is a 1. The order is a 1 in both cases. Now, what does this order overall tell us? If it's second order overall, and I know that I double both, what's double times 2? Again, it's 4. So it is helpful to know what it is overall to give us a general idea of what we can do to speed it up and how fast that will do things. Okay. So here's another equation. Now this has a very interesting thing. Check this out. How many reactants do we have? Yet how many are in our rate equation? So let's talk about the order of each reactant from our rate law that was experimentally determined. Okay. Hydrogen peroxide is first order. There's a 1 there when we don't write it. Iodide ion is second order. Now notice how it certainly does not match the coefficient. It's not meant to. Okay. But then where's the H+? Well, the H+ is not shown because the H+ is 0 order. And remind me of your math. Anything raised to the 0 power is 1. So that reduces away to 1. So what's it mean to be 0 in order? Well, that means you can change the amount, the concentration of that reactant all you want and get no change in the rate of the reaction. Now, is that reactant necessary? Apparently, yes, it is. It's part of the reaction. But in this case, you could double it and there'd be no change in the rate. You could triple it, no change in the rate. You could put in half as much, no change in the rate. It is important for the reaction, but it is not going to affect how fast the reaction occurs. So what would happen to the rate if the concentration of everything was doubled? So if I doubled peroxide, that's a 2. If I doubled iodide, that's a 2. Now this peroxide's 2 is raised to the power of 1. This iodide's raised to the power of 2. And then this, if we want to, we can. Let's say we double the hydrogen ion. It's raised to the 0. Now let's simplify. This is 1. So we're going to now ignore that. So 2 times 2 squared. We'll do the square first. So that's 4 times 2. We get 8. Okay. So 8 is the effect of doubling everything. 8 times as fast if we double everything. And really it's only if we double the hydrogen peroxide and the iodide. We really don't need to double the hydrogen ion in order to get that rate change. Okay, so things I want to tell you about K. Because we've been talking about K, rate constant. Things you need to know about the rate constant. This is very important. They very well could ask literally just a basic, do you understand what K is, type of question on the test. So these are very important things to commit to your memory and not forget. And these, I don't like that you memorize something, but these are very useful. You will use these things so much that commit them to memory now, and then eventually you'll just be used to them and you don't necessarily need to have them memorized because you'll just know them. So K, lowercase k, is the rate constant, and it can only be determined experimentally. Knowing the balanced chemical equation will not be useful. This is interesting. The units, the label of K will change depending on the overall reaction. And we'll come back to that thought much later on. Okay, I have examples, and it's not difficult, but just know it will change. K does not change if the concentrations change. What changes is the numbers here, not that number there. It also doesn't change as time changes. If we're like starting the reaction and I come back 2 days later and I want to know what's the rate now, well, these concentrations have changed as the reaction has occurred because reactants get used up in a reaction, but K would not change. K does change based on temperature. Would the concentrations change if I, say, increase the temperature by 10 degrees? Well, no, but we just know from the earlier lesson, a change in 10 degrees almost doubles the rate. So then what's the only thing left that could change? The K. This K is the only thing that could change based on temperature. So you have to specify temperature or assume, unless you're told otherwise, that it's 298. That is standard temperature of 25 degrees Celsius for these reactions. Only gas laws have a standard temperature of 0 degrees Celsius. Now, why we can't pick a standard for everything, I don't know. I know that we don't have a standard for everything because the gas law people didn't talk to the rate law people. But why we can't now go back and just retroactively say, hey, we're going to pick 25 or we're going to pick 0 and use it for everything, I don't know. But we just haven't. So assume it's at 298 Kelvin. That's a capital K for Kelvin. Unless you're told otherwise, and that is 25 degrees Celsius. K does change if a catalyst is added. Again, what's a catalyst do? Well, a catalyst does not change concentrations, but we do know it speeds up the rate. So how would a catalyst then change the rate if these are all the terms I have in my equation, and that is to change the K value there. So that K is very important, and it is very important to know what would change that K value and would not change that K value. That is something to have in your head very firmly, very decidedly, knowing, yes, this will, no, this will not. Maybe make a little T-chart real fast in this, back of your notes of what will change K. And here's the things that yes will change it, and here's the things that no will not change it or something, okay? Know these principles in your head, know them well. Okay, we're going to come up to some examples where we actually determine the orders experimentally, like we're going to pretend we're scientists and we've done some experiments and now we have data, so now we can figure out what the rate is. But this is a topic for another time. What I wanted to impress upon you so far today was the vocabulary involved. Know the vocabulary. We call these exponents orders. Okay, we talk about A is to the X order, B is to the Y order, C is to the Z order, whatever that number is. We talk about the order overall. You add it up. And know that K, the rate constant, and it's a lowercase k is the rate constant. Know what does and does not change that lowercase k. Okay, so that's where we're going to stop for today. Good luck on your assignment, and I will see you again later.